In this video, we will talk about how to find the derivative of a vector-valued function. So in the previous video, we had this function r of t, which equaled ti hat plus 4 minus t squared times j hat. Or in component form, we could write this as t as the first component and 4 minus t squared as the second component. So what I would like to do is have a way to take the derivative of this function. Okay, so I want to give a definition for what the derivative of a vector function would be, but I also want to, alongside it, draw the picture so we can visualize what this derivative might represent. So we've seen that the graph of this is this sort of upside down parabola. At least when I draw all of the vectors, all of the position vectors, their heads all lie on this parabola. Okay, so now let's define the derivative function. So the derivative, so r prime of t, has a really similar definition to the derivative of a regular function, a scalar function. It's the limit as h approaches 0 of r of t plus h minus r of t all over h. Okay, so I'm going to box this. So this is the definition of the derivative of a vector-valued function. So it turns out that when we use this definition, our derivative rules that we're used to from calculus, they apply. And in practice, the way I take the derivative of a vector function is, it turns out we end up just taking the derivative of each component. Okay, so if we use this limit definition of the derivative, we can show that all the derivative rules from calculus apply if we wanted to. I'm not going to focus on that. Instead, I just want to talk about what the derivative represents visually and do examples where I take the derivative. So in practice, to do that, I just take the derivative of each component. So in our example, let's do that. In our example, r prime of t is going to be equal to, so the first thing that I have to do is look at the I component and then take its derivative. So the derivative of t would be 1. So that would be the derivative of t, and then I'll have that I hat. And then I look at the j component, and the j component of my original function is 4 minus t squared. We take its derivative, which is negative 2t. Let's put that, let me mark it in blue just so I can see what matches up with what, and then j hat. And that's the derivative of my vector function. I just take the derivative of each component one at a time. All right, so let's plug in a few values into this. So what if I take r prime? Whoops, I forgot to put a prime here. So I forgot to put a prime on this r. Okay, so this should be r prime of t. This is the derivative function here. All right, so now I'm going to plug in 1 and plug in 2 to see what we get out, and then talk about how we can visualize these. So if I plug in 1, well, I'll still get the I hat. There's nothing to plug into there. I just get the 1 in front of the I hat. And then if I plug in to the next term, I'll get minus 2 j hat. If I plug 2 into this, I'll still get I hat in the front. And then the next term will be minus 4 j hat. All right, so in our picture, let's recall what r of 1 and r of 2 were. So r of 1, the position vector, was 1, 3. And r of 2, if we plug that into the position function, was 2, 0. Oops, sorry. I got to put a vector brace around this. Okay, so if I draw those position vectors, r of 1 looks like this. R of 1, and r of 2 will go to this point here, 2, 0, and that is r of 2. So those are our position vectors. But now let's draw these derivative vectors. So if I draw in r prime of 1, which is 1 comma negative 2, I'm going to draw this vector. R prime of 1, so that its tail is where the head of the position vector was. So I'm going to draw the tail emanating from here. So I got 1 in the x direction, negative 2 in the y direction. That's going to be something like this. That is r prime of 1. That's the vector 1 comma negative 2. And if I do the same thing with r prime of 2, I'm going to draw its tail where the head of its corresponding position vector is, where r of 2's head is. And then I draw the vector 1 comma negative 4. This one is sloping more downwards than the first vector that we drew, so maybe something like this. So that is r prime of 2, and that's the vector 1 comma negative 4. And looking at these vectors, these look like tangent vectors. They look like they might be tangent to the curve. Okay, and it'll turn out that they are, but I want to show that. I want to show that they are going to be tangent to the curve. Okay, so before we do that, there's a question that I want to ask. So in this setup, if r of t is the position, if it's a position vector function, then is the derivative velocity? Is r prime of t velocity? In the same way that we're used to seeing from calculus, the derivative of position when we talk about scalar functions is velocity. Is the same thing true for vector valued functions like this? So to answer that, we need to check the magnitude and the direction. So we need to check the magnitude and we need to check the direction. So I need to check the magnitude of r prime of t and the direction of r prime of t and see if they match up with what they would be for the velocity vector. So for the magnitude, what we'd be looking for is we need the magnitude of r prime of t to be equal to the speed, because that's what the magnitude of velocity is supposed to be. And then for direction, we need the direction of r prime of t to be tangent to the position curve. Okay, because if we have a bug or a particle that's traveling along this curve, so if it's at a point here and then it starts traveling along it this way, traveling along it, once we get to a point like this, r1, its movement right at that instant would be tangent to the curve. Same thing if I go a little bit further. If I go a little bit further and I stop it at r of 2, its a movement, if we were to sort of like let it go and just let it continue in the direction that's moving most immediately, it would sort of go tangent to the curve. All right, so we are hoping that the direction of our derivative function is going to be tangent to the position curve, just like the velocity vector is. All right, so now let's check these. So let's do magnitude first, and then we'll do direction. So let's first check magnitude. So I'm going to do this more generally. I'm going to start by saying, what if r of t is a general vector function that looks like x of t comma y of t? Then its derivative, r prime of t, would be the vector function where I take the derivative of each component. So I'll get x prime of t comma y prime of t. All right. Or if I wanted to, I could write that in the dx dt notation. So this is dx dt comma dy dt. I could also write it like that. All right, so now let's take the magnitude of this. So the magnitude of r prime of t is going to be the square root, and then I square each of the components, and then I sum them. So we'll get dx dt being squared added to dy dt being squared. So remember, that's how we find the length of a vector. And we've seen this before. We've seen the square root of dx dt squared plus dy dt squared back in section 11.2. We saw this term. And this term was the speed. That's what we saw in section 11.2. So, and the speed is the magnitude of the velocity. So what we've just shown here is this r prime vector function. Its magnitude is the same thing as the magnitude of velocity. And that's good. That's what we were hoping for. We were hoping that it had the same magnitude as velocity. So this has the correct magnitude. So it has the same magnitude as the velocity function. All that's left to check is, does it have the same direction as the velocity function? Because if it does, if it also has the same direction, now that we know it has the same magnitude, those two things combined would mean it is the velocity vector function. All right, so let's talk about direction. So I'm going to draw a picture. So I'm going to draw a picture. I'll have some axes. And I'm going to draw that parabolic path. So the parabolic path, and I'm really going to focus on just like one quadrant here. So I'll focus my picture mostly on one quadrant. But my parabola would extend infinitely this way, and it would extend infinitely that way. And in this picture, what I'm going to do is I'm going to take sort of an arbitrary position vector along that path. So I'll take a position vector like this, and I'll call this r of t. Okay, and then I'm going to take a position vector that's a little bit further along the path. So a little bit further along the path. And this one's going to be r of t plus h. So we're at this green point at the head of this vector after t plus h, whatever the units of time are. And then we're at the blue head of that vector after t units of time. Okay, so as in this picture, I'm going to let, and now I'm going to form one more vector in this picture. So I'm also going to draw a vector that connects the head of r of t to the head of r of t plus h, and I'm going to call that delta r. So that's the change. I'm calling that the change in r. All right, so in this picture, I'm letting this vector delta r be such that r of t equals the vector delta r. Whoops, sorry, one mistake there. So what I meant to say here is r of t plus that vector delta r. So if I go along this vector r of t, and then I go along the vector delta r, that equals the vector r of t plus h. So using the geometry of how we add two vectors, adding r of t to the vector delta r is going to equal r of t plus h. All right, so now let's isolate for delta r. So delta r will be equal to r of t plus h minus r of t. And now the reason why I'm doing this, the reason why I'm isolating delta r is what we end up with on the right-hand side is starting to look like the definition of the derivative. It's just missing the h on the denominator, and it's missing a limit. So let's start to put those things in. So if we divide both sides by h, I would get r of t plus h minus r of t divided by h. If I divide by h on the other side, we get 1 over h times the vector delta r. Times the vector delta r. Okay, so looking at this equation, 1 over h is just some number. It's called a scalar. Right, so we've seen that term before, scalar. That just refers to something that's just a number, not a vector. So because this vector that I have on the left is equal to a scalar times this vector delta r that we have on the right, that means those two vectors are parallel. So this fractional thing that on the left is parallel to this delta r vector on the right. So the final thing that I have to do to actually get the derivative vector is, now we have to take a limit. So as h approaches 0, we are going to get that this vector, this delta r vector, the smaller h gets, the closer that h gets to 0. So as we start taking points on the curve that are closer and closer and closer to the head of the vector rt, that delta r vector will be tangent to the curve. So we are going to get a tangent vector. Okay, so the right-hand side is going to become a vector that is tangent to the curve. The left-hand side is the derivative. So we are getting that the derivative is equal to a tangent vector. Okay, so this means that we have the correct direction. Correct direction. Our derivative is going to be pointing in a direction that's tangent to the curve. Okay, so because we have correct direction and correct magnitude, this means that r prime of t equals v of t, the velocity. So the derivative position, the position vector function, is the velocity vector function. Okay, so I'm going to highlight this. All right, so now there's something I want to note about this. So in the last video, I sort of posed the question, is this particle that's traveling along this path moving faster at t equals 1 or t equals 2? Now that we know the derivative of r is velocity, we can use the velocity to answer this. So if I take v of 1, if I plug 1 into my derivative function, we end up getting 1 comma negative 2. All right, and if we plug in 2 into our derivative function, we end up getting 1 comma negative 4. So that we had done earlier in the video. Earlier in this video, we had done these two things, plug in 1 and 2 into the derivative function. Now let's take their magnitudes, because we want to know which is faster, so we want to know which has the bigger speed. So the magnitude of v of 1, if we work this out, it's going to be square root of 5. If we work out the magnitude of v of 2, that one works out to be square root of 17. So this one is larger. This one is larger, which means the object is moving faster at t equals 2. So the object is moving faster at t equals 2 than at t equals 1. All right, so we can use the velocity vector to determine things like the speed of it by taking the magnitude of the velocity vector. All right, so I want to sum up some of the key things that we've said. So when we talk about a function r of t that equals x of t, comma y of t, comma z of t, so this vector function, this is called a position vector function. So we label a position vector function as r of t typically. When we take the derivative of that position function, r prime of t, and to do that computationally, we just take the derivative of each component. So we get x prime of t, comma y prime of t, comma z prime of t. That equals v of t, which is the velocity vector function. So the derivative of the position vector function is v of t, velocity vector function. And what we just showed is the velocity vector function is tangent to the position curve. So by position curve, I mean if you take all of your position vectors, like this blue vector r of t, and this green vector r of t plus h, and you trace out the path made by the heads of those vectors, that gets this position curve. That was this upside down parabola in our example. When we draw the velocity vectors at the points on that curve, when we draw the velocity vector at the points on that curve, the velocity vector will be tangent to the curve. All right. All right, two other things that I want to just summarize. So speed, we've seen this before. Speed is the magnitude of the velocity vector. And the magnitude of the velocity vector would be dx dt squared. So that's the first component squared, plus the next component dy dt squared, plus the next component dz dt squared, all being square rooted. All right. And that is equal to, we saw in section 11.2 that this is equal to dl dt. So this is from section 11.2. So what is L here? So remember that in this equation, L represents the arc length. So we saw in section 11.2 that the derivative of this arc length function, dl dt, looked like this. It was the magnitude of the velocity vector. It represented the speed of the particle. Okay, and then finally arc length. This is also just reviewing a little bit from section 11.2. It's an integral. It's an integral from a starting time a to an ending time b, and it's the magnitude of v of t dt. All right, so these first two things, what r of t equals position function, what r prime of t equals velocity function, are new to this section. And then these second two formulas for speed and arc length, they're connecting stuff that we've seen in this section with stuff that we saw in section 11.2. Alrighty, so the final thing that I want to comment on is if we took the derivative of r twice, the second derivative r of t would be the first derivative of v, and the derivative of v is a of t. It's the acceleration, kind of how we'd expect. So this is the acceleration, and it's a vector function. So the outputs would be vectors here. Okay, and the convention is if we needed to draw this acceleration vector function, if we wanted to draw this, we would draw the tails at the heads of r of t. So we draw the tails at the heads of the position vector function. And that's the same thing that we do when we draw the velocity. So in terms of our goals for this section, we have defined the derivative of a vector valued function, and we've talked about what that means graphically. In the next video, we'll do an application of these vector functions to projectile motion.